You may recall this example from learning about how when you have an E2 reaction and you have two different types of beta hydrogens, you might observe deprotonation of both types. So we observe deprotonation of beta prime to make the more substituted product, and what I have labeled as beta to make the less substituted product. And we said, hey, the more substituted is more stable, and that's what's observed, especially when you use a nice slim base like potassium ethoxide. Okay, that was great. Did anybody notice how these numbers only add up to 80%? Yes, you thought I was crazy, right? Well, there's another product. Can you predict it? Haha, it's this. This is the product. So this ether product is formed. Where does that ether product come from? Yeah, it's tricky, right? It's a substitution product. Ethoxide is a base, it's a nucleophile. It can be both. You know, when we started this discussion of substitution and elimination reactions, I said, yes, so substitution, you react with some nucleophile Y. Elimination, you react with some base B minus. But guys, these can be the same thing, right? And so I've mentioned a couple of times there can be competition between substitution and elimination reactions. And that's why we keep talking about rate. And that's what we are seeing here. We're seeing that the SN2 competes with the E2. So we have some SN2 product and we have some E2 product. The E2 reaction seems to be faster. It's made up the major part of the product mixture, but we see some SN2 product as well. It's just the minor product for this particular reaction. And that's because ethoxide, it can be a base and it's a nucleophile. They act pretty similarly. Bases accept protons, nucleophiles donate their electrons. They react similarly. And so the same species can do both things. Yeah, okay. Are we having a panic attack? How are we going to predict whether or not a reaction will be SN2 or E2 elimination? Well, one of my friends came up with a pretty ingenious method for doing this, and if you just force yourself to do it, you're going to get 100% of the questions that I ask you. And by the way, I'm the one writing your questions. You'll get 100% of those questions correct. So when you're trying to decide for E2 versus SN2, we're going to employ what my friend calls good, fair, poor. And all we're thinking about here is the reaction rates. So G is going to be good. That's going to mean that we have a fast reaction. Fair, F, that means we're going to have a moderate rate of reaction. And P for poor will have a slow or no reaction. So we've talked about the rates of the SN2 and the E2 reactions and all the factors that affect them. And you can go back and you can list all the factors that affect those reactions. And you can drive yourself crazy thinking about every single factor. But we can really boil most of these reactions down when we're considering SN2 reactions to just first start with the sterics of the alkyl halide, right? So thinking about the alpha carbon, the one that's being attacked. So we're going to have a good rate of SN2 if the alkyl halide is methyl or primary. Fair if the alkyl halide is secondary, and poor if the alkyl halide is tertiary or if the nucleophile is very bulky. So this is where we have to, use our chemical intuition and look at other factors too. So not everything is going to boil down to just the sterics of the alkyl halide, but we're going to start there. And then for the rate of the E2 reaction, we're going to focus on the base strength. This is going to be important. It's going to require a strong base like we talked about 45 minutes ago. So we're going to have a good or fast rate of E2 if the base is as strong or stronger than than hydroxide. So the conjugate acid of the base has a pKa greater than or equal to 16. We'll have a fair or moderate rate of E2 if the conjugate acid has a pKa in between that of water and hydroxide. So the conjugate acid pKa for HB, it's in between 0 to 16. And you're going to have a poor or slow rate of E2 if you have a weak base. So the conjugate acid pKa is going to be less than 0, meaning that the conjugate acid is a strong acid, and you know strong acids have weak bases. So weak base is not going to do an E2. Just not going to happen. So let's practice. We're going to look at these reactions and we're going to rate both possible mechanisms, SN2 and E2, and then predict the predominant reaction pathway, identifying the major products of each reaction. If there is an important minor product, we will identify it. You're welcome to try this on your own, or you're welcome to listen to me the first time, and then there'll be one more page of problems you can try on your own. It's up to you. So remember, for SN2, we are looking at the sterics of the electrophile first, and for E2, we're looking at base strength first. So we have a methyl halide here. We know methyl halides are excellent SN2 substrates, right? So good rate of SN2. E2, we have hydroxide. This is a strong base, so this would technically be a good E2 as well. But guys, there's no beta carbon, so it's not possible to have an E2 here. So we're going to have an SN2, and we can go ahead and draw the mechanism for fun. So attack, displace, and we end up with methanol as our product. So this is our the substitution product will be observed. Awesome. Next, same deal. We have a methyl halide. I'm so lazy, I'm going to copy and paste. We have a methyl halide and we have a strong base. So we might say this is good for both reactions. This is good for SN2 and it's good for E2. Well, again, E2 cannot happen because methyl halides don't have a beta CH. There's no beta carbon. There's only the alpha carbon. So again, we're going to have an SN2 here. So we're going to have this ether product. Okay, let's just show you where the carbons are going. So there's that methyl right there. Okay. So substitution products are fun, right? We had an alcohol, we have an ether. The functional groups can really vary depending on what your nucleophile is. Okay, so now we have a primary alkyl halide that is still good for E2. We're reacting it with hydroxide. Hydroxide is the conjugate base of water. Water has a pKa of 16. So hydroxide is a good base, strong base for the E2. So we have a fast rate of E2 as well. So there's a tie. So what do I want you to do? In the case of a tie, as long as you have a decent nucleophile, I want you to choose SN2 as the major product. So we do have a decent nucleophile. So we're going to have our major product is the substitution product. But we are going to have a significant minor product since they tied. So we are going to have some elimination to form this alkene. So that's our minor product. So one more time. They tied. I want you to predict SN2 as long as this is a decent nucleophile, which it is. And then you'll have some minor E2 elimination product. All right, let's look at the next example. So we have the same alkyl halide. So we know that it is primary and good, fast rate of SN2. This time we have cyanide though. We know cyanide is an excellent nucleophile, so that's going to definitely enhance the argument for SN2. We need to think about the pKa though of HCN because that will help us determine whether or not the E2 is good, fair, or poor. You've memorized this. The pKa is about 9 or 10. And so that means we are in this 0 to 16 range for the conjugate acid of the base. That is a fair or okay, I guess, rate of E2. Good, fast SN2, but only fair E2. So that means the SN2 is the major product. So we would have cyanide, displaced bromide, and we have our substitution product. All right, so hopefully you can kind of see what I'm doing here. And go ahead and try yourself now. We have 3 more chances for you to try, and I promise we're almost done. So I've identified the substitution patterns of the alkyl halides here, looking at the alpha carbons. And the primary alkyl halide will have a good rate of SN2, and the secondary alkyl halides will have fair rates of SN2s. So they'll have moderate, but it will be much slower than a methyl or primary halide. So then let's go ahead and evaluate E2. So we have an alkoxide base here. So alkoxide bases are good bases for E2, and that's because the pKa of their conjugate acids, alcohols, is 16. So weak conjugate acids, strong base, this is a great base for an E2. So this will be a good E2. So at first glance, it looks like they tied, right? But if you recall what we said we were going over the good, fair, poor here, is that you're going to have a poor SN2 if the halide is tertiary or if the nucleophile is very bulky, right? So what we're proposing happening if we propose an SN2 here is with this super bulky nucleophile, right? I've taught you in the E2 lecture to recognize that T-butoxide is bulky. So actually that slows down the SN2 and makes it poor. This oxygen is just so crowded with those methyl groups, it just cannot get in here and displace that. Or I mean, it can, but it has a high activation energy. So instead of SN2, E2 wins, and the major product will be the elimination product. So we will eliminate beta hydrogen, and we will have the alkene as our major product. Excellent. Let's keep going. So for the secondary alkyl halides, for our next 2 examples, the SN2 is definitely slowed down. So it's only fair. Let's take a look at hydroxide. Hydroxide is a strong base. It's an excellent base for the E2. So this E2 is going to be considered good, a fast rate of E2. Good is better than fair, faster than a fair. So we will have the E2. There are 2 beta carbons, but they're exactly the same. This molecule is symmetrical. So we're going to get an alkene product. Actually, the same exact alkene product we got before. So just to make sure, and we rotate the molecules, it can get confusing, but here are the atoms. I've just rotated it. All right, last example. So same secondary alkyl halide, still going to be a fair rate of SN2. Now, I have this time used cyanide. So cyanide's conjugate acid is HCN, has a pKa of about 9 to 10. Okay, that's not negative, that's about. So that means that this is a weak acid. However, we have defined when the conjugate acid has a pKa between the strengths of hydroxide and water, so 0 to 16, that this will only have a fair rate of E2. It's just not a strong enough base. It's okay, it's a moderate base, I guess, based on pKa, but it's not that strong. And it is an excellent, excellent, excellent nucleophile. So that really breaks the tie. And we have SN2 happen here, even though it's a secondary halide. This is still a great SN2 because cyanide is a great nucleophile. And there is our substitution product. Okay. Not so bad, right? So I want you to think about how we're able to predict the products of reaction of an alkyl halide with a base nucleophile. It's tricky, right? When we first introduce these reactions, like, oh, Y minus is a nucleophile versus B minus, that's a base. But here's the deal. They can often be the same thing, right? We saw in the previous examples, we saw hydroxide act as a nucleophile. We also saw hydroxide act as a base. So I want you to think about what you have learned about how to choose between E2 and SN2. In fact, let's return to this example that we started with and just see if we'd be able to use good, fair, poor to predict that the E2 products would be the major products. E2 is the major pathway. In other words, E2 is faster than SN2 for this particular combination of molecules. Let's see if we could have predicted that using good, fair, poor. Now remember, for good, fair, poor, we recognize that we have an alkyl halide. We recognize that we have something that can be a base nucleophile. So you say to yourself, okay, this could be a substitution or an elimination. So for SN2, you want to evaluate the sterics of the alkyl halide. So this is, if we look at the alpha carbon, this is a secondary alkyl halide. If you want to, go even further, you say bromide, that's a good leaving group, but you don't need to do that. You have a secondary alkyl halide. So this is going to have a fair rate of SN2. It's going to be slower than methyl and primary. Now you see the base nucleophile, you said, okay, this could have an E2. I need to just ask myself, is it a base? Because if it's not, then maybe it's going to act as a nucleophile instead. So remember, we have defined whether or not it's a good base in an E2 as relative to hydroxide. So you want to look at the conjugate acid of ethoxide, and that's ethanol. And you want to think about the pKa, that is 16. So we have said when the pKa of the conjugate acid is greater than or equal to 16, this is a good base for E2. So E2 would be fast. So this will be a fast E2. It's a good base. It's a strong base. And yes, we would have predicted E2 wins, and E2 is the major product. E2 elimination products are the major products. Okay, got it? So you can see that you can do it. You can even predict this stuff that seemed scary at the beginning. So now it's time to go and do some more practice.